All right. So first, I completely forgot about thioacetals and did not include them on the 16 handout. So let's do it now quickly. So thioacetals are the exact same as normal acetals, except instead of an alcohol, you have the sulfur thing, the style group. It does the exact same thing as the alcohol would do. It's just going to go in and attack the carbonyl and then add itself. So if we have an excess thiol with the carbonyl, then we just do the same thing as the acetal and add the thiol twice onto the carbonyl carbon. Then if we have a molecule that has two thiols on each side, then we can do the same thing as like a cyclic acetal. So you're just going to attack the carbonyl carbon with both sides of the molecule and then get a cyclic thioacetal. So the carbonyl oxygen goes away and you just get that cyclic sulfur thing placed right on top. Yeah, it's technically a ketal. The thing with acetals is that you can be specific and call acetal or ketal, but as like a general functional group, an umbrella, they're called acetals.
What is the
Thio?
on campus?
Yes, it's on Canvas.
What's it called?
Exam 3 review. The only important thing with thiols, the only way they're different than like your normal acetal, is that they're used to completely reduce aldehydes and ketones. So once we've made a thioacetal, we can just give it this thing called radionickel. If we give it radionickel and hydrogen gas, it just cuts off the sulfur groups and replaces them with a hydrogen. So we're going from like a thioacetal to a plain alkane. You just count the ones in between. So there's 2 here and then 2 up here. Yeah. From this thing back to the carbonyl? Probably water. I don't know. I think so. I don't know. If it's on the SI sheet, it was probably not on the exam. Okay. A kind of important concept for this chapter is like reactivity of carboxyl derivatives. This will probably like straight up be a question, just like asking you to rank all of these. So what's the most reactive out of all the derivatives? Yeah. Acid core is the most reactive, and then not carboxylic acid, acid anhydride. Because remember, these are ranked based on like the goodness of their leaving group. So the chloride has the best leaving group. The chloride ion's pretty good. And then you have this like carboxyl ion for the anhydride as the leaving group, which is pretty stable. Then what's next? The ester? Yeah, ester and carboxylic acids are like the same. And then that just leaves amide because the NH2 group is not a good leaving group. All right, so going to the problems, we'll come back to the first one. We'll start with the second one first. So I'm giving you an ester and then water with an acid catalyst. So what happens there? Yeah. So with these, with carboxyl derivatives, you find the leaving group and then you find the nucleophile and then you can just cut and paste. So get rid of the leaving group and add your nucleophile where it was. So this alcohol goes away and you replace it with the water to make a carboxylic acid. And then I'm telling you the first step of this, I guess, transformation is Sockle 2. And then the second step, we don't know. So after the first step, Sockle 2 just turns it into an acid chloride, right? So now we have to find out what takes an acid chloride, what's going to make it go to an ester, and that one specifically. Yeah, we're just going to add ethanol to this. So this nucleophile that we added over here to replace the chlorine leaving group is an ethanol group. So we just know our nucleophile that's missing is that. All right, let's go to the third one. So we got some kind of beta keto thing, and then we're giving it water. So it turns into carboxylic acid again. This structure is called your beta keto acid. And what reaction can beta keto acids go through? So if you have a beta keto acid, you can just basically cut the acid part of it off and leave it or let it leave as a carbon dioxide. Then the reagents you need to do that are these. The lithium hydroxide, DMSO over like some kind of heat and acid. And then all that happens is that the carboxyl group gets cut off and deprotonated, and you get a ketone and carbon dioxide. All right, let's do the first one now. So this one, I gave you a starting product and an ending product, and there's like 3 steps in between that we have to figure out. So what was the total transformation that happened in the overall reaction? Yeah, you took an ester, added this thing, and it got turned into an alcohol. So what reaction do we know happened somewhere in the sequence? Water? That was probably part of it, yeah. You do not. Yes, you do use a reducing agent. There would be a Grignard, yeah. So because we replaced this leaving group with like an alkyl group, you know that we used a Grignard to make like the alkyl group nucleophilic. So we know at some point in this reaction, we used the Grignard. We have gone straight from this molecule to that molecule with 1 Grignard step. Why not? I can't hear you.
Yeah, final product of first step, then the second one, linear.
The first step Grignard,
No.
the
final
second,
product.
yeah, the second step is going to be the Grignard.
This one, final product.
No, it's not thionyl chloride. Because first of all, this is an ester. I don't think thionyl chloride works on esters.
Problem with ketone.
Okay, so when I saw this problem or was writing it, I was like, okay, so in the final product, you have an alcohol, but it's not tertiary. If we have like a carboxylic acid or an ester, anything with a leaving group and do a Grignard on it, it becomes a tertiary alcohol. So the first addition, you get rid of like the leaving group, and then the second addition, you get rid of the other pi bond. In this case, there was only room for one addition, which means we got rid of the leaving group at some point in the reaction. So I know there was a reduction somewhere. So at this point, I know there's going to be a Grignard at some point, and there's also going to be a reduction. The other thing I noticed about this problem is that this ketone was left untouched. And then what can we use as like a protecting group for ketones while we do stuff to other molecules? That would be for alcohols. So to protect ketones and aldehydes while you mess with other stuff, yeah, you're going to use a cyclic acetal protecting group. So here's what I know so far. This is secondary, which means it was reduced into an aldehyde or ketone before we did Grignard. If we went straight into this with Grignard as an ester, it would be a tertiary. But I know that we reduced it into an aldehyde before doing Grignard, so we could get a secondary alcohol. So I know a reduction happened. And if we did a reduction of the ester, it would have reduced the ketone as well. So what makes the most sense is to protect the ketone, then reduce the ester, and then do the Grignard. So the first step, we said to protect the ketone, you would use like the diol to make a cyclic acetal. So this effectively protects the ketone. So now we can mess with the ester and do whatever we want to it, like reduce it, and then the ketone stays untouched. So now what do we do with the ester? An aldehyde, yeah, or ketone. Exactly. So we're going to reduce this into an aldehyde before we do the Grignard. So the way to get an aldehyde from an ester is to use dibol. I'm pretty sure it's only dibol. The other weak reducing agent is for acid chlorides. So after dibol, we get this molecule. So we have an aldehyde. Now, if we do a Grignard to an aldehyde, we will get a secondary alcohol because there's no leaving group. So what Grignard reagent did we use here? An ethyl? Yes, we use an ethyl because this nucleophile that we added in the end is 2 carbons. So we know it's just going to be an ethyl with an MGBR. And then lastly, I didn't write this, but like the very last step would be an acid workup. And then what the acid workup would do is protonate the alcohol and also restore the acetal back into a ketone. It's just the diol and then some kind of acid catalyst. Okay, so that problem was kind of ridiculous. You're definitely not going to get anything like that, but like this kind of idea will be on the exam, like reduction, protecting groups, Grignards. So yeah. All right, let's move on. So first up, nitrile diball water. What happens? Yeah, so diball H and nitrile just turns the nitrile to an aldehyde. And then now what's this reagent called? From Wittig's? It's a phosphonate. Well, phosphonate esters for the other one is called an ylide. So whenever you see the PPH3, it's going to be an ylide. When you see an ylide, you know that you're going to be doing a Wittig, which means you're just going to be copying and pasting some stuff. So when we have a Wittig reaction, what do we copy and paste? Yeah, so all we do, we cut off the oxygen of the aldehyde or ketone, and we cut off the PPH3. And then I just take this R group and then replace the oxygen with it. So cut off the oxygen, take the R group attached to the phosphonate thing, and then slap it on this double bond right here. So my final product is going to be that. Maybe one thing you have to be careful with is like activating the ylide, I guess. So before, like, this is considered the active reactive form of the ylide because it has the double bond. Then the double bond means that this is a carb anion down here. You just need to make sure that like that carb anion is there, so it's ready to react. Like sometimes he'll give you the unreactive form, and it would be like pH, triphenyl. And then everything would be like happy and protonated. There'd be no charge on the carbon, no double bond. It's not reactive. So in this case, you need to give it like a strong base, like NaH, to deprotonate this carbon and then make it reactive. Okay. So the next one, what do we have in the molecule that could do something? Yeah, so we have 2 alcohols and 1 ketone. So 2 alcohols plus 1 ketone. gives you an acetal. Yeah, the just interesting thing is that it's intramolecular. So you make intramolecular rings. Do you want to draw the product? I don't know if these is gonna work. I think this is better bet. Yeah, that's perfect. They just turn into two 5-membered rings. Sticker. So it's this one. All you need to know is that when you have an aldehyde or ketone and then alcohols, the alcohols just go and stick themselves onto the carbonyl carbon. So we know that both of these are just going to wrap around and attack this carbon. Then you can count like the ring members. Yeah, then get your final product. So the original like ketone carbonyl thing is gone, and now we just have our new acetal OR groups there. This. All right, so next, ketone MCPBA, what happens? Yeah, so you're gonna add an oxygen on either side of the ketone. And then the only thing that you're gonna be like tested on about this is like the order of preference for what you wanna add in between. So the order goes like, you wanna add the oxygen between the carbonyl carbon and an hydrogen. And then the next preferable is a phenyl. Then it's like your standard like tertiary, secondary, primary, whatever. So keeping that order in mind, which side does the oxygen add? Right side. It's going to add between the carbonyl and the phenyl. Okay, so, oh, and this is called Baeyer-Villiger oxidation. I don't know if that's important, but yeah. So next, I've given you this Horner-Wadsworth-Emmons transition state. And then the HW transition state is like identical to the Wittig one. The only difference is like the stuff attached to the phosphorus. So in Wittig, you have 3 phenols attached here. but in Horner Wadsworth Emmons, you have like a bunch of oxygen groups. So this whole thing, like this P or whatever, it's called a phosphonate ester. That's like the real difference between the two mechanisms. Otherwise, they do like the same thing. By the way, the important thing to remember about this transition state is that these substituents from the aldehyde side, the substituents from the phosphonate side are going to be trans. So hint, hint, remember that those are always trans in the transition state. Because you want to get your E alkene as the final product. And if they're like di-substituted things, like if there was some other stuff down here, the biggest groups would be still trans to each other. But yeah, anyways, from the transition state, what do you think the final product is going to look like? The final alkene.
So have a double bond, and then one side of the double bond going one way is going to be ethyl, and on the other side, it's trans going to be propyl.
Yeah, that's perfect. So yeah, with the transition state, all you need to do, you just have to cut it down the middle. So there's two parts of like the transition state, two halves. The top half is the half you're concerned with. It's like the R groups that are bonded in the final product that we wanted. The bottom half is just like the side product, whatever, the oxygen phosphorus stuff. That is not important. So what we're going to do is cut it down the middle between the oxygen and phosphorus bond and then the R-R bond. And we're just going to cut it and put a double bond between each side. And that's how you get your final products. So the top half gave us this R group alkene as our final thing. And the bottom half, we get our oxygen bonded to the phosphate, whatever. And I doubt you'll get like a question on this, but I think I saw it once. Like he'll draw the arrows in the transition state and make sure you got them right. The thing to note is that, well, there's only one real important arrow. It's from like this carbon phosphorus bond. It's gonna go down here. And then this side, this like carbon oxygen bond flips up to go up there. And that's what actually forms the two double bonds. He's usually never picky about mechanisms or transition states. I think this is like the only ones. Okay. So what's next? So we have a benzene and then this stuff. So what reaction? Friedel-Crafts. So it's Friedel-Crafts, we know acyl chloride, acyl alkyl halide. You cut off the halogen part and put a carbocation on it. That's what the Lewis acid catalyst is going to do. So we've established the electrophile now. Then where on the benzene are we going to add the acyl group? It's going to be para to the alcohol. So looking at the directing effects, the alcohol directs ortho-para, so it's here, here, and here. And then the methyl is directing mostly ortho. So it's going to be those two. So there's two carbons that have like a lot of directing effects going towards them. They're very nucleophilic. But the thing is, we never really add meta between two substituents because it's sterically not favorable at all. So in these situations, we just go with the most unhindered one, which is para to the alcohol. So we just go ahead and attack, and then we get a ketone. So we've established a ketone, and then we're giving it some kind of amine over an acid catalyst in the next step. So what does that form? Yeah, no, it's not hydrogen. It's secondary. Secondary makes an amine. So this is just enamine formation. You don't really have to be concerned with the names as long as you like recognize the functional groups. Yes, whenever we have an aldehyde and a ketone plus a secondary amine like this, it's going to make an enamine. And as a reminder, the enamine functional group looks like this. So the secondary amine on top, and then this like bottom half down here is what the original carbonyl was. So it's like we just went from, wait 1 second. So we went from our ketone, gave it a 2' amine, and then get this as the enamine product. The interesting thing about enamines is that as opposed to like an imine or oxime, whatever, those have double bonds, like a CN double bond. In this case, there's no space for a CN double bond because it's a secondary amine. So when you do your elimination to like resolve the extra hydrogen or something, it's gonna go on the side. So it's gonna be like an alpha double bond. Yeah, and then you have to pick the side that's going to be more stable on. So on the original ketone, because an enamine looks like this in the final product, you know you're going to add a double bond on either side of this just to like make the functional group. And then we're going to add it on the isopropyl side because it's more stable. But also, since the double bond is formed through an elimination reaction, you need a hydrogen atom to do an elimination. So whichever side you pick has to have a free hydrogen on it. So in this case, you do have a free H, so you will make the more stable one. But if this was like a terbutyl group, you no longer have that extra hydrogen and you'd be forced to put a double bond over here. So considering that, what does the final product look like for this problem? Mhm. Yes. So remember, we cut and paste, get rid of the oxygen, put this entire thing on it, -1 hydrogen, and then find out where to put the double bond.
The right side?
Yes, the right side. So now that we've copied and pasted, we know our double bond is going to go somewhere. It can't go on the left side because there's no free hydrogen on this carbon. So we can't possibly form the double bond via elimination. So we have to put it on this isopropyl side. And it's like very good because it's tetra substituted. And that's your final enamine product.
That's the conjugate, right?
It is conjugated. And remember, you have the lone pair from the nitrogen, so it's like extra conjugated. All right, so next, ketone plus what? And then you have an acid catalyst, and then you get this final product. So what's missing over here? And amide? Yeah, some kind of amino. So this exam is the exam of copy and pasting. Whenever we see something that happened like this, we know we cut and paste something onto the oxygen. So then we just see like what we pasted, add 2 hydrogens onto it, and then you get your nucleophile CV. So in the end product, we have an NOH. So we know that our missing thing is going to be NOH plus 2 hydrogens. In the process, you just lose 2 hydrogens. So this group, the H2NOH, is called hydroxylamine. And you should recognize aldehyde or ketone plus hydroxylamine gives you this final functional group, which is called an oxime. All right, next we got, the exact same reaction again. So this is Friedel-Crafts. We already know the product of this because we did it like a minute ago. So we know we get some kind of ketone product. So we have a ketone, and then we have this set of reagents. Wait, let me add water. So this set of reagents, this top thing, which might be important, this 2 amines bound to each other, it's called your hydrazine. So yeah. So normally if you have just a ketone plus a hydrazine, you get a hydrazone, which looks like this. Remember, cut off 2H, copy and paste. This thing is your hydrazone. But in this case, we have more stuff on the bottom, which tells you it's what reaction. It does. So this is a reduction of the ketone. It's your Wolff-Kishner reduction. Wolff-Kishner, and then the other one, which is called Clemmensen. The reagents for Clemmensen are like ZnHC over HCl. Both of those, you take a ketone, you cut it off, it turns into a CH2. When you see the set of reagents plus ketone, we're just going to get rid of it. No more carbonyl, just an alkyl.
Does it lose the alcohol?
Like from here. Oh, I first forgot to draw it. Okay, so for the enamine's case, there's only one free hydrogen. The rest of these follow like the 2H thing. Enamine is the exception for like the double bond and the hydrogen thing. All right, so next, ketone, and then what's the set of reagents? It's the diol. So distant bond line looks like this, and then you get what from that? You get your cyclic acetal. Then we get the cyclic acetal acid. So what happens then? Goes back into the exact same ketone. All right, so here, ketone, and then what's this stuff? It's HWE. You can tell because you have this phosphorus stuff with a bunch of oxygens. That is a giveaway that it's a Horner-Wadsworth Emmons. So for both HWE and Wittig, what's really important is that you have this carb anion on the carbon adjacent to the phosphorus. You have to form that to make the reaction possible. In this case, there is no carb anion. So if it was deprotonated and this was an active phosphonate ester, we would have this thing deprotonated, or there would be like a double bond here. But we don't see that, so we know that the NaH is there to actually turn the phosphonate ester into the active reactive form. But because we have the NaH there, we can just pretend that it's reactive and then go ahead and do the reaction. So this is the exact same principle, cutting and pasting. So all I do, I just draw like a double bond between the phosphorus and carbon. And then I cut off the oxygen of the carbonyl. I take this R group and then paste it where the oxygen was. So the final product of this, you get like the pentagon and then the alkene is still there. The pentagon on one side, your alkene, and then the R group of the phosphonate ester, which would be this. It's the exact same thing. The only difference is the stuff on the phosphorus. All right, so I had a question about this, but it's like pretty far down in the handout, so I'll just mention it now. The thing with these, for phosphonate ester and ylide preparations, you have your like phosphate group with stuff attached to it, then you have to give it an alkyl halide to actually make the ester or the ylide. So what he does sometimes, he'll give you all the steps of the Wittig or the HWE, and then what's going to be missing from the entire reaction is the alkyl halide. So in this case, if he gave you like this final product and I don't know, like the transition state, maybe you would just have to like find the answer of what alkyl halide was used to make this phosphonate ester. So in this case, it would be something like that. And then the phosphorus thing would just go in and attack, get rid of the bromine, and then you have your technically unreactive ylide or ester. So there's like 2 steps in yliter ester formation, attack the alkyl halide, deprotonation by strong base.
When it connects to the cyclopentane, we don't use the carbon that's directly attached to the phosphorus?
No, you do not, because I guess that is just like this carbon in the final product.
No, that's the carbon with the double bond.
Yeah, it's like 1/2 of the double bond. It's like when you draw out the square transitions, it makes sense.
Oh, I see.
Yeah, deprotonate with strong base. All right, that
could have been on bromine.
yeah. Usually bromine, but it doesn't matter. That is all the time we have. There's not much left, so I'll just finish it on Thursday.